First of all, I would like to make a summary of the linear dynamic system here represented with their transfer function in the Laplace domain, of course. So you remember we have studied the first order system which has this transfer function. I remind you that the transfer function is just defined as the ratio in the Laplace domain between the output variable and the input variable. So it is just a definition. The transfer function is the ratio between the output variable and the input variable, both considered and defined in the Laplace domain. The transfer function has two parameters, Kp, the process gain, and tau p, the time constant. S is the Laplace abscissa, and the transfer function is first order because S appears at the denominator only with degree 1. And you remember that the general behavior, the general pattern of such a system when considering bounded input is self-regulating. It means that if the system is at a steady state in a qualitative way, self-regulating, autoregolante, means that if the system is at steady state and is perturbed, is disturbed in a bounded way, so without a disturbance which is of infinite size, so it is perturbed in a finite way, then it will reach a new steady state after some time. Then we have studied a special case of the first order system, which is the purely capacitive first order, in which the parameter in the transfer function is just one, the gain, the process gain, Kp, and the trailing coefficient is lost. Means that the denominator contains the Laplace abscissa only. This is the purely capacitive or pure integrator, purely capacitive first order or pure integrator system. And we learned in our past course that it is non-self-regulating. So it may happen that for some bounded inputs, after some time, the output response is going to infinity. Then we have studied the second order system, which has a second degree polynomial in S at the denominator, and has three parameters: the process gain, Kp, the natural period of oscillation, tau, and the damping factor, zeta. And this is again a self-regulating system. And finally, we have studied the dead time, or pure delay, which is completely different from the previous one because it has a transfer function which is not a rational function. So it is not expressed as a ratio of polynomials in S only, but as a transcendent functional expression. The pure delay has a transfer function which is the Neper number raised to minus TdS, where Td is a time and is just the dead time or pure delay. And again, this is a self-regulating process, but later we will learn that it is the main cause or stability loss in feedback controlled systems. At open loop, it is a self-regulating. But when put inside a closed loop configuration, we will learn that it is the main cause of destabilization. And finally, we have the transfer function of the PID controller with the three actions: the proportional, Kc, the derivative, tau ds, and the integral action, 1 over tau is. Whereas here the three actions, proportional, derivative, and integral, are just added. Now, for such systems, we have already introduced the concept of BIBO stability. BIBO is an acronym indicating bounded input, bounded output. So, an unconstrained linear system is said to be stable if the output response is bounded for all bounded inputs, for all, careful, all bounded inputs. So you cannot test just one input, for instance, the step input. You have to test all the possible bounded inputs to conclude that the system is BIBO stable, because you are observing a bounded or limited output response for each and all of the bounded inputs. If just one of the bounded inputs is generating an unbounded, so an infinite output response, the system would not be BIBO stable. Unconstrained means that the system is an open loop, so there is no feedback or no other complicated manipulation of input and output variables. Linear means that the corresponding mathematical model in the time domain is a linear ordinary differential equation. And as a consequence, the system is described, can be described in the Laplace domain by a transfer function. Because you know the Laplace transformation can be successfully applied if and only if the time domain system is linear. Otherwise, if such a condition is not met, the system is BIBO unstable. Look, I anticipated by my words. If just one bounded input results in an unbounded response. The mathematical criterion for BIBO stability I took this from the book from Seborg, is stated here. A necessary and sufficient condition for a linear dynamic system to be stable is that all the poles of the system transfer function have negative real parts. I have to remind you that the concept of pole. Pole is the root of the equation, of the characteristic equation. The characteristic equation is obtained by taking the characteristic polynomial. Polynomial is just that at the denominator, and setting it equal to 0. So in such a case, the characteristic polynomial is tau squared s squared plus q zeta tau s plus 1. This is the characteristic polynomial. I set it equal to 0, and I obtain the characteristic equation. I solve the characteristic equation. In such a case, it is the classical second degree algebraic equation in S. I obtain Q roots. The Q roots are referred to as poles. So, a necessary and sufficient condition for a linear dynamic stability system to be stable is that all the poles, not just one, all the poles of the system transfer function have negative real parts. Most industrial processes are stable, are BIBO stable without feedback control. So they are said to be open loop stable or self-regulating. An open loop stable process will return to the original steady state after a transient disturbance. By contrast, there are a few processes, such as exothermic chemical reactors, that can be open loop unstable. So, as a consequence of this necessary and sufficient criterion, we can look at the location of the poles of the transfer function. And their location gives us immediately an idea about the open loop stability of the system, the BIBO stability properties of the system described by that transfer function. So, if the transfer function of a dynamic system has even one pole with a positive real part, the system is unstable. So it means that the left, poles can be located on the complex plane, where we have the real axis and the imaginary axis. Because in general, poles are complex numbers. So the left half plane is the locus of BIBO stable systems, whereas the right half plane, this one, is the locus of BIBO unstable systems. The imaginary axis is the boundary, and the boundary has special properties. Stable region, unstable region. In fact, we have to define, this is something new, the concept of marginal stability. An input-output system is defined marginally stable if only certain bounded inputs will result in a bounded output. Look at the difference. Here we are stating that only certain bounded inputs will result in a bounded output, whereas we have said before that for a BIBO stable system, all bounded inputs must result in a bounded output. This latter case occurs when there are poles with single multiplicity on the stability boundary. A further property of a marginal system is the following. A marginally stable system may exhibit a special behavior in its output response. In that sense, the output response neither decays nor grows. So it means that there is no. It means that it is bounded. Neither decays nor grows, is confined within a certain interval. It is bounded. Okay, but it may remain strictly constant or may display a sustained oscillation. So let's be more precise about self-regulating processes. Taken this definition from Stephanopoulos, a self-regulating dynamic process is such to seek a steady state operating point if all manipulated and disturbance variables after a limited change are held constant for a sufficient length of time. So the self-regulation is a definition related to the property that the system have to seek and to remain stuck on a new steady state when all disturbances, all changes in the input have been terminated. Here we can, although on the screen they are quite small, we can look the different behaviors of the systems, because here we are considering in all cases a step input, and we are looking at the effect of such a step on various systems. You cannot easily read, but you can easily understand after my words. Here we have a second order systems with two real poles. Look, they are here. Two real poles with two negative and real poles. So they are located on the negative part of the real axis. This is a BIBO stable system, and the step response is this way. So it's the classical S-shaped response. It's the sigmoid. In the second case here, we again have a second order system, but we have a couple of complex conjugate poles with a negative real part. Again, this is a BIBO stable system, but the process response is oscillating. You know, this corresponds to the case you have studied earlier of the so-called underdamped system. Here in the third block, we have the denominator is s squared plus 9. So we have a couple of purely imaginary conjugate poles. We have two poles with opposite imaginary part, or just located on the imaginary axis. In such a case, when you apply a step input to the input variable, you change it according to a step. A step is applied in all cases. You are getting a sustained oscillation. Means that the amplitude of this output response curve remains constant with time, and the oscillation frequency remains constant as well. But the input was just limited, was bounded, and was applied just at one time instant, and not changed anymore. In spite of this, the output is continuously oscillating. This is an example of marginally stable system. And finally, there is the critically damped case. So here we have two poles, both negative and equal. So we have a pole with a negative pole with multiplicity equal to 2. Again, this is an example of BIBO stable. So here we have three BIBO stable responses, because the system is BIBO stable, and one example of marginally stable system. Next time we will start from here. I reproposed to you the reference cases for the process, but starting from the next time, we will consider the process inserted in the classical feedback control loop configuration, in which we have to add a sensor to measure the process variable. We have a reference value for our controller variable that you know is the set point. We will add a controller. We will, for the moment, we will be focused on PID controllers only. And the controller action is able of moving and determining a control action on a manipulated variable by means of a final control element. You learned that the most common final control element in the process industry is a control valve, is a regulating valve. And so now we have to study, but we have time and many lectures to do this, how the closed loop will influence and will perturb the BIBO stability properties of the process taken in the open loop. So we will investigate how closing the loop will heavily affect the open loop BIBO stability features of our process.